start.
Hi, everyone. Welcome to our monthly seminar. Today, we're so excited to have Dr. Cheng-Hau Yang. Dr. Yang is a postdoctoral researcher at Argonne National Laboratory, whose research focuses on advancing modeling techniques within unfitted finite element frameworks for complex microphysics systems. His work develops robust, scalable formulations for large-scale parallel simulations, particularly within frameworks such as MOOS. He has collaborated to both fundamental methods, including the shifted boundary method and finite cell method, in practical simulation tools for advanced manufacturing. Dr. Yang received the 36th Robert J. Melosh Medal, a prestigious student award in finite element methods. Please join me in welcoming him. Dr. Yang, the floor is yours.
Yeah, thank you for inviting me to the talk. And yeah, and my basically I'm Cheng-Hau Yang, and I'm a postdoc in Argonne National Lab, and I just graduated from my PhD last year. And the presentation topic is from geometry to physics without boundary fitting meshing, multi-physics simulation on complex domain. And thanks for my collaborators, Bhaskar and Aldash. They are my PhD supervisor, and Guillermo Kovaci is my collaborator at Duke University, and he's also the inventor of the shifted boundary method. And thanks Gary and Mark, they are my supervisors at Argonne National Lab. So why we want to use the non-boundary fitting method? So this is the scenario. We want to use a non-boundary fitting meshing. It's really good for these kinds of simulation. So for example, if we have the geometry, the CAD geometry, and based on the geometry, we are going to create the boundary fitting mesh around the geometry, and then we go to perform the CFD simulations. However, the process from the geometry to the meshing is a time-consuming procedure. So for example, if we have a CAD geometry, we may facing some intersected surfaces. So this some human efforts to clean out the geometry correctly. The other thing is that we may face some small features of the geometry shape. Then this needs lots of human efforts in creating the mesh around these small features. And if we want to, for example, sometimes after we perform the simulation, we need to go back to, based on the simulation resource like the jet coefficient, we need to go back to design our geometry again. And then we go over this procedure again to create a mesh. It will be very time consuming. So that's why people invent the immersed boundary method. So the idea of an immersed boundary method is that we can have the mesh, and the mesh can be totally independent of the geometry. Then we do not need to have lots of human effort spending on creating the mesh. It will make the total workflow smoother. So if you look at this, one is time consuming to create a mesh. The other is little to no effort. However, if we have the boundary fitting mesh, for example, in the CFD simulation, most of the time we want to apply the no-slip boundary condition. We just need to go to the nodal point to apply the boundary condition strongly there. How can we apply the boundary condition on this immersed boundary mesh? So that's why we use the shifted boundary method. So the shifted boundary method is invented by Professor Kovaci in 2018. The idea of the shifted boundary method is that it tries to shift the boundary condition from the true boundary, the real geometry boundary, to the surrogate boundary. And the surrogate boundary are made out of element edges or faces. So because we want to shift the boundary condition, then suppose the real boundary condition on the true boundary is u equal to g. Right now, we should not apply the u equal to g also on the surrogate boundary. We should apply u equal to g tilde. And we can calculate the distance from the surrogate boundary to the true boundary, which is D. And based on this D vector, we can do the tertiary expansion to get the form of the G tilde, which is G minus gradient U dot D. And after we have the form of the G tilde, basically we use Nietzsche's method to apply the boundary condition on the surrogate boundary. So it will be, let me use this pointer here. Yeah, so if you look at the Nietzsche's method over here, we will have the consistency term and the joint consistency term and the penalty term. And basically we will plug in the form of the G tilde here. Then we can get the form of the shifted boundary method. So most of my PhD work and my postdoc work are focused on extending the shifted boundary method. First of all, shifted boundary method is unlike the other immersed boundary method. The other immersed boundary method, it applies the boundary condition on the true boundary, so it's exact. However, the shifted boundary method will have the flexibility to choose the surrogate boundary. So this gives us some idea, could we have the surrogate boundary, which we call optimal surrogate boundary, can help us reduce the error in the shifted boundary method. The second point is that Professor Kovaji, when they created the shifted boundary method, they apply it mostly to the triangle or the tetrahedral discretization. How about we apply the shifted boundary method to the upstream mesh? Then we can apply the local adaptive mesh refinement and local mesh refinement way more easy. And the third point is that shifted boundary method mostly go to deal with the problem of the single phases problem, like the flow problem or the structure problem. How about we apply it to the multi-phases problem, like the thermal flow problem? And the fourth, the last point is that when people do shifted boundary method, they mostly apply the shifted boundary method to the isotropic linear elastic model. How about we apply to a more complex model like the crystal plasticity model? And on the bottom, this is the simulation to showcase some of the this feature I mentioned above. So here you can see the slingshot is moving inside the fully domain. And because the slingshot and the background mesh is discretized using the arctree, so we cannot use the traditional method to apply the boundary condition strongly. We should use the shifted boundary method to apply the boundary condition. And when the slingshot moves inside the fully domain, you can see it will generate some vortex. And based on the adaptive mesh refinement, we can actually put more mesh at the a vortex region to do the adaptive mesh refinement. And this is the one-way coupling fully structured interaction. So it can be also treated as the multi-phases problem. So basically the simulation, the presentation can be summary as making shifted boundary method more accurate through the optimal surrogate boundary, and making a shifted boundary method more efficient through the arctree and adaptive mesh refinement. And the last is making shifted boundary method more broadly applicable through applying to the thermal flow problem and the crystal plasticity problem. So the first part, we talk about the optimal surrogate boundary. So when Professor Kovaji, they first invent the shifted boundary method, they try to remove all the cut element. So basically, here you can see there's no cut element in the surrogate domain. And the surrogate boundary will be within the true boundary. And when Kumar-Sarwar did the shifted boundary method, he tried to keep all the intercepting element. And here the surrogate boundary will be outside of the true boundary. This gives us some ideas that could we do not discarding all the intercepting element. We also do not keeping all the intercepting element. We try to keep some and retain some. And the idea is that we can build a surrogate boundary that the distance from the surrogate boundary to the true boundary can be a minimum. And because of some of the error from the shifted boundary method is from this tertiary expansion, if we minimize the distance from the surrogate boundary to the true boundary, we should able to reduce the error in the shifted boundary method. So basically, we come up with a way to build out different surrogate boundaries. So the idea is that we calculate the true domain occupied fraction on the Cox cell. And if this true domain occupied fraction is larger than 1 minus lambda, we try to keep the element. In our terminology, we call this element true intercepting element, means this element should be involved into our computation. And basically, we pick lambda from 0 to 1. And this is an example. Basically, we will do a point in polygon test to mark the background element. So you can see the background element is all the quadrilateral element. And by the true boundary, which is this red curve, we can mark element as the out element, which is this white element, and the in element is this green element, and the intercepting element. The intercepting element means that some nodal points within the true boundary, some nodal points outside of the true boundary. And based on this true domain occupied fraction, if we pick lambda equal to 0.5, we can fully classify the cut element to the true intercepting element and the false intercepting element. So the true intercepting element here will be the yellow element, and the false intercepting element here will be the this blue element. And the true intercepting element should belong into our computational domain. So here we mark this as in, and the false intercepting element should be not so false. So we mark it this as out. So the in domain will become our surrogate boundary, and between the in and out, we can have our surrogate boundary. So when we pick a different lambda value, we can generate different surrogate boundary. For example, if we pick a lambda equal to 1, the surrogate boundary will be outside of the true boundary, which is the same as the Kumar's approach. And if we pick a lambda equal to 0, the surrogate boundary will be within the true boundary. This is the same as Professor Scovaggi, his first approach. Then actually, if we pick a lambda from 0 to 1, we can build our different surrogate boundary. And then if we pick a lambda equal to 0.5, we found that this surrogate boundary can give us the minimum root mean square distance from surrogate boundary to the true boundary. And we are going to test whether this lambda equal to 0.5, this minimum distance from the surrogate boundary to the true boundary can minimize the error in the shifted boundary method. So here's the problem of the Stanford bunny, and we solve the Poisson equation. And on here, you can see the L2 error, and you can see at different lambda value, lambda equal to 0.5 can give us the smaller L2 error compared with the other lambda values. And the other thing is that we also test for the incompressible flow simulation. This is the full pass and airflow problem. And if we look at the pressure profile over the airflow, and you can see that lambda equal to 0.5 can give us the smoother pressure profile. However, if we go with the other lambda value, it will have some oscillation of the pressure there. So the idea of the shifted boundary method is that we can deal with the complex geometries with easily. We do not need to spend lots of time to create a mesh. So we're able to run the full simulation of flow passing through gyroid. So you can see the streamline try to detour inside the gyroid, and we're also able to solve the Poisson equation on the Eiffel Tower. And the second part of the presentation is making shifted boundary method more efficient through the upstream mesh and adaptive mesh refinement. So this is mostly the same as the other adaptive mesh refinement approach. And basically, we try to calculate the vorticity, and based on the vorticity magnitude, we can know which region we want to refine more, which region we want to do the coarsening. And after we have the mesh, after the refinement and coarsening, we can project the solution from original mesh to the mesh with refinement and coarsening. And here's the different part if we want to apply adaptive mesh refinement with a shifted boundary method. For example, in this case, originally the mesh is very coarse, but with more information, we will refine the boundary a little bit. And because of the refinement of the boundary, we should update the surrogate boundary. Then we can apply the boundary condition correctly through the shifted boundary method. And then we go to the next time step. And here's the example. On the left-hand side is the meshing. On the right-hand side is the Q criterion. So the Q criterion is basically measuring how much rotation of the Foley particle. And you can see that when we have a larger Q criterion, we also have more mesh to capture the full structures. And based on this approach, we do not actually need to refine all the wake region. And if we try to plot the x direction velocity on the wake region, you can see that our resource goes to the literature result. And the third part is about making the shift boundary method fully applicable to the thermal flow problem. So basically, we solve the two-way coupling problem. Inside the Navier-Stokes equation, after we solve the Navier-Stokes equation, we'll get the velocity. And we can pass the velocity to the heat transfer equation to become the convection velocity in the heat transfer equation. And the heat transfer equation, we solve to get the temperature, and we pass the temperature to the Navier-Stokes equation to become the buoyancy force. So this is the example. This is the weak form. And basically, we go with BDF2 as a time integrator. And you can see that on the Navier-Stokes equation, we have this forcing term. So basically, this forcing term is based on the temperature. And on the heat transfer equation, the convection term, you can see we also have the velocity here. The velocity here is what we get from the Navier-Stokes equation. And this is one example. This is a natural convection problem. And on the star shape, we apply the hot temperature. On the background, we apply the ambient temperature of T equal to 0. And you can see that the hot temperature here will creating the buoyancy force going up. And so the flow is going up. And with the different Rayleigh number, you can see that the flow will become more complex and more turbulent. So basically, this Rayleigh number, if you take the square root of it, it's like the Reynolds number. Yeah. So in my previous presentation, I'm mostly talking about the problem we have complex geometry, like the complex boundary geometries. Like the flow passing through geroid, we have the complex boundary, and the Stanford boundary problem, the boundary we want to solve for is very complex. However, in some problem, the boundary of the domain is very straightforward. However, inside the blocks, it may have some complex interfaces. So actually, we can also use shifted boundary methods to the problem here. Instead of shift the boundary condition, we shift the interface condition. So this is like the shifting interface method. And most of the time, the interface condition we are interested in is the Robin type interface condition. So basically, on the left-hand side, this is the derivative. And on the right-hand side, it will be the function of the jump of the variable. And this can be applied to the thermal contact problem. For example, if you have the jump over the interface, then you can use this jump over the interface to calculate the flux between the interface. And the second thing is the cohesive zone model. Based on the displacement, based on the gap between the interface, we can use this to calculate the traction between the interface. And I will focus on this more. And if we shift this, we have the shifted cohesive zone method. And why we care about the cohesive zone modeling? Because we want to perform the grand scale modeling. And why this grand scale modeling is needed? This is because when we try to look at the 3D printing metal sample, if we zoom into different part, if we look inside the microscope, we can see that each part are made out of lots of tiny grains, and these tiny grains will affect the local stress and local damage, and also the creep evolution. So if we want to actually predict the pretty correctly, we actually need to have the grand scale model to connect microstructure to macroscopic simulation. So basically, FEM is taking care of the macroscopic simulation. And to deal with this grand scale simulation, we mostly will focus on the crystal plasticity simulation. And these have three important components. One is the grand boundary damage, and cohesion zone master and shifted cohesion zone master were able to take care of this. And the other part is linear incompressible plastic flow, and the third part is the history dependent stress response. And I'm going to talk more about how these two related to the shifted cohesion zone method. And basically the cohesion zone method, like what I mentioned earlier, is it try to describe the section separation law. So on this part, you can see on the bottom, it describes the separation. And based on the separation at the beginning, if the separation become larger and larger, the traction also become large. But after some stage, you will go into a softening stage. It means that the displacement become larger, however, the traction will become lower. Yeah, so for the nearly incompressible of some of the elements inside our simulations, we actually need to have the numerical method to treat it properly. If we do not treat it properly, we will suffer from the volume locking. So this means that some of the elements, it will become stiffer and become very hard to deform. So this is an example. The blue dot here is the one has suffer from the volumetric locking. So you can see that at the same loading time, it becomes stiffer, then the reaction force will become higher than the normal one. And the normal one, we can apply the volumetric locking correction to let the element deform correctly. And people mostly use F-bar approach and B-bar approach to do the volumetric locking correction to deal with the volume locking problem. And for the volumetric locking correction, if we want to go with the first order finite element basis function, it does not work for the triangle and the tetrahedral element. It only works for the first order quadrilateral and the hexahedral element. So we actually try to creating the mesh using the tetrahedral element and the hexahedral element. So if we try to create a mesh, like the interface fitting mesh using the tetrahedral element, we can actually create this very easily using the G mesh. However, if we want to create using the tetrahedral element, we will face some issues that actually the final mesh we created is not the actual interface fitting mesh. We have some wavy shape on the interface, even though we go with the very sophisticated meshing software, Qubit and Sculpt. So that's why people may use adaptive mesh refinement to refine the interface. But this will cause the degrees of freedom to grow a lot. And if we forcing the meshing software to create the real interface fitting mesh, we will suffer from the other issues that some of the element will have the negative Jacobian, and this is not, we are not able to solve it using the finite element method. So because creating the heterohedral mesh for the our solid mechanics problem is very hard, so it actually motivates us to use the shifted cohesion zone method to deal with these kinds of crystal parasitic problem. And the same as the shifted boundary method, if we want to apply the interface condition in the shifted cohesive zone method, we also need to build our surrogate domain and surrogate interface. So the way we build the surrogate domain is from this. For one element, it may be occupied by different gram, and basically there will be some gram occupy the element more. For example, in this case, gram 2 occupy this element more than the other grams. We'll basically just mark this element as gram 2. And this is an example in 2D. We have the true boundary and the true gram, and based on the true gram, we can mark the element. So we'll have the surrogate grams, and between the surrogate grams, we can have our surrogate interfaces. And the 3D is the same principle. So after we have the surrogate domain and surrogate interface, we can apply the shifted cohesive zone method. First of all, we talk about the cohesive zone method. So basically, this is from times the strong form with the test function and doing the integration by part. So we will have the jump of the test function and also the times with the cohesive zone section. And for the shifted cohesive zone, because we shift the interface condition from the true interface to the surrogate interface, as a result, we should tune the condition a little bit with the n dot nh term. So this the first n is the true normal, the second n is the surrogate normal. I will talk about this term later. It can help us correct the boundary condition. And because actually, if we want to do the integration on the surrogate interface, this effect should be the same as the effect on the true boundary. Then because we do the normal decomposition here, we will have some remaining term to add. Then we will have the same effect as the boundary term in the cohesive zone method. So the first problem we test is the manufacturer solution problem with the linear isotropic problem. And we try to test different interface condition. One is the shifted cohesive zone. The other is we naively apply the cohesive zone on the pixel lattice mesh. So we can see that one converges very well, but the other it does not reduce the error after refinement. So the reason is that this area correction term, n dot nh term, if we actually remove this term, for example, we do the integration only on the surrogate interface, then actually the error we will get will be the rectangle parameter. However, if we add this term in our formulation, we can actually get the real circumference of the circle. So this it can expand why without applying in the shifted cohesive zone, the error is 0.1, means that it does not change with the mesh refinement level. Because no matter how we refine the mesh, if we do not put this term, the only things we will get is the parameter on this rectangle. We only do the integration on the rectangle, then the traction will be applying will be wrong. So we also test the problem with the single interface problem, and here we try to pull the material, and we try to plot the momentum stress over the diagonal length. And you can see that the shifted cohesive zone method match very well with the interface fitting mesh. If we remove the direction correction term, you can see that the resource is also close to interface fitting method, but the resource is a little bit off. And if we naively apply the cohesive zone method here, the result is way off. Yeah, and we also test the problem for the real microstructure. Here we have 37 grams, And we also try to pull the material. And you can see that the average damage and also the reaction force with respect to time. The shifted cohesive zone method all match very well with the interface fitting method. And so we want to extend the simulation from the isotropic elastic to the crystal plasticity. For the isotropic, the stress response is very straightforward and easy. We have the stress vector and the strain vector. So basically, the strain vector just need to times with the elastic stiffness metric to become the stress. However, in the plasticity, there are lots of internal variables. For example, there will be hardening, there will be electric strain and orientation we need to calculate. And the relationship and the calculation between them is very complex. So that's why my supervisor at Argonne National Lab, they invent the NEMO2 simulation framework. They're able to decouple this complex crystal physics into modular building blocks. And how is this related to the shifted cohesive zone method? Remember, we have the direction correction term. Because we have direction correction term, we need to evaluate the stress on the surrogate interface. As a result, this means that we also need to calculate and do the material update on this surrogate interface Gauss point. And we start with the easy problem, the problem with single interface again, and we try to pull the material. And in the sense what we observed previously, the shifted cohesive zone method match very well with interface fitting mesh. However, if we do not put the direction correction term, is a little bit different here. And if you just naively apply the cohesive zone method, the reaction force will be way off. And this black frame is the interface fitting mesh. And the background pixelating mesh is the shifted cohesive zone method. So also, if you look at on on the displacement, they also match very well with each other. And the next, we test for the 3D problems. And we try to apply different cohesive zone parameters between the interface. And the same as previously, this black frame is the interface fitting method, and the transparent one is the shifted cohesive zone method. So you can also see that they match very well with each other. And for like if we calculate the quantity like the maximum damage over the loading time and reaction force over the loading time, IFM and SCZM match very well with each other. Yeah, we are also able to deal with the problem of the deal with the multiphysics problem. So basically, we will grab more interface condition here, which is the thermal contact problem I mentioned earlier. And we solve two physics. One is solid mechanics, and the solid mechanics will pass the displacement to the heat equation. And so basically the displacement will be at the denominator here. This means that when the displacement between the interface become larger, then the heat transfer between the interface should become smaller. And also the heat transfer equation will pass the temperature to the solid mechanics problem. Basically, we will use the temperature to calculate the thermal expansion. And you can see that when we have the small conductance value, the conduction between the interface will become very small. That's why when we pull the material after a long time, the temperature jump between the interface is become large because there is no heat going from one side to the other side. And if we have the large conductance value, because we have a strong heat conductance between the interface. That's why the temperature close to here is like the linear temperature changing. And one thing I want to say here is that which I try to pick non-physical thermal expansion value and conductance value, but I just want to showcase that we're able to deal with the multiphysics simulation using our framework. Yeah, the last part is that because shifted boundary method, we do not need to have lots of human efforts to create a mesh. As a result, we are easy to perform lots of simulations. So this is an example of we perform legion cavity simulations of a complex geometry and full passing pass complex geometry simulations. And right now we are in the AI age, and some of the AI workflow, for example, the AI will lack of some simulation data point, then it may need to call a physical simulation backend to run the simulations. And shifted boundary method is really suitable for that because it does not need human efforts to create the mesh. Yeah, so in the conclusions, we make the shifted boundary method more accurate through the optimal surrogate boundary algorithm and making shifted boundary method more efficient by applying the shifted boundary method to the uptree with the adaptive mesh refinement and making it more broadly applicable to the multi-phase thermal flow problem and the shifted coherence zone method applied to the crystal plasticity problem. And also, also the shifted boundary method is very suitable for the AI workflow because we can run the simulation automatically. Thank you for your listening, and thanks for your attention.
That was a great talk. Thank you so much, Dr. Yang. Are there any questions from the audience? If not, I can start with the Q&A. How sensitive are SVM, SIM methods to complex geometries or sharp interface features?
Yeah. So, sorry. I also actually prepared slides for that. Yeah. So, this is a good questions. So, it will starting more. And so in my experience, if we go with the actually simple shape, like the circular disc, if we want to apply the shifted boundary method, actually the surrogate boundary will become actually very complex and pixelated. And we are able to deal with this problem properly. And so if the shape of the original true boundary shape become very complex, then this is the same because always the surrogate boundary will become very complex. And the second point I want to mention is that the local mesh refinement is very important. So for example, if you have the true boundary like this, and if you do not refine the mesh properly, then you cannot actually capture the wavy shape changing here. You actually need to have more refinement over here. And the same as the other finite element method, like if we have the boundary there, we actually need to have more refinement over there as well. And the last part is that people may talking about the distance function calculation on these complex geometries. For example, if this point, you may find the distance from to element to H1 or H2. Actually, this slightly different calculations difference will not affect the resource a lot.
Thank you so much. My next question is, how difficult is it to extend SVM, SIM to highly nonlinear material behavior, like fracture or large deformation?
So for example, if this is the fracture problem, Professor Kovaci and his students already done this problem previously. Is the shifted fraction method. So the idea is the same as the shifted cohesive zone method, but it just apply the cohesive zone method on the fracture interface. Yeah, and the other thing is that if we want to do the large deformation plastic problem, actually our framework already try to do this. So basically, we have the Nemo2 framework, like what I talked about previously. It's taking care of the history dependent response. We also have the Moose framework is taking care of the large deformation. And if I want to talk about how the difficult part is to implement the large deformation plastic, I will focus on, well, like what I talked about previously. We also need to have the material updates on the Gauss point on the surrogate interface, and if we want to deal with this, we need to modify the Moose code a lot. And the other thing is because you talk about the nonlinear material behavior, then we actually need to use the Newton method to solve the problem. Not only we will have the residual make sure we solve the real problem, we also will have the derivative of the residual, make sure the solver can solve properly for this problem. And actually calculate this derivative is a little bit hard, and it takes me lots of time to implement this.
Thank you so much. Are there any other questions from the audience? If not, I'm going to switch gears. What has been the biggest challenge in developing these methods?
Yeah, so basically we need to identify the gap between the negative framework and the method requirements. For example, if I want to implement the shifted cohesive zone in Moose, I need to taking care of the parallel computing. For example, inside the Moose, lots of code can run parallelly, means that we can use MPI run to run it. Then if I try to implement the code, I should not break the MPI run. And the second thing is that inside Moose, they already have lots of existing framework capabilities there. For example, inside Moose, it have some mesh generator capabilities. So we can actually tackle this to build our background mesh. We can also tackle this to read the boundary mesh. And also inside the Moose, it also can taking care of the interface integral. Then I just need to inheriting from the interface integral to implement the shifted cohesive zone method. And the missing part, for example, like what I'm showing inside the talk, is that we need to build a surrogate interface, surrogate boundary, surrogate domain. And also we need to do the distance and normal calculation. This is not inside the original Moose negative framework. So we should implement this. And also, like what I mentioned earlier, the Jacobian of the like the derivative of the residual is very hard. But right now, I think AI can help a lot to help you try to see whether you implement this correctly.
Thank you so much. I want to also ask you about your experience at Argonne National Lab. How has it been so far since you graduated?
Yeah, so yeah, I will say that in Argonne National Lab, I can yeah, my work is very large, has lots of difference than my PhD works. My PhD works is mostly focused on CFD, and my work here is mostly works on computational structure mechanics. And I really feel like in Argonne, I can interact with many talented scholars, like my supervisor and my colleagues. I actually learn a lot with them every day. And also in Argonne, there are also experts from different field, like the material expert, factory expert, air expert. So yeah, I think we can learn a lot here. And so basically, Argonne is at Illinois, and it's very close to Chicago. So yeah, I very encourage you guys, if you have a chance, yeah, you can consider applying for the intern or the postdoc here. So yeah.
And do you have any advice for the graduate students in computational mechanics?
So this is actually what my supervisor talked to me during my PhD and my time in Taiwan. And so I will say that write down the equation here before you start the implementation. So we deal with lots of PDEs and deal with lots of boundary conditions. We should write down everything very clear and derive the weak form and use the numerical scheme to do the discretization and write down the what should be what should be the mass after we do this. And when we do the implementation, we just need to follow the mass correctly. And the second thing is that do not treat yourself as the user. Consider yourself as the developer. So for example, inside our simulation, we may have lots of input file. We can tune the Reynolds number, Rayleigh number. We can tune the mesh. We can tune the order of the basis function in the finite element method. So, but some of the people does not know what's this parameter actually used inside the code. We should actually try to understand what's this parameter read inside the code and fall inside the code, and is it going inside integration, is going inside assembly, or is mainly used for the post-processing? Then if we change the parameters, we can get to know what we actually change for our simulation. And the third point I would say, talk to people and do not hesitate to ask questions. So for example, at the beginning, I have collaboration with Professor Kovaji. So the reason why we can have the collaboration with him is because when I first implement the shifted boundary method in our own in-house code, actually I cannot get the correct resource. So basically we just send an email to him, and after that email, we start lots of collaboration after that.
Thank you so much for a great talk and for your answers. We're going to be looking forward to your future publications. And we also want to thank our audience for being here today. Thank you again and have a good day.
Thank you.